That was awesome, Sasha. I didn't know what Sasha was going to present, so I'm going to repeat a little bit of it, but he really hit it out of the park, if I may say so. There'll be like 6 more dad jokes tonight, so just get ready. Okay, so he kind of went into money a little bit, but this is like a really important... So like money is the first application that came along with this blockchain protocol technology. It was coupled with Bitcoin, and then we realized, like, whoa, this technology that's allowing us to have money can be extracted a little bit and create things like Ethereum, which isn't necessarily just money, it's code and smart contracts. But the history of money is, it's like thousands of years ago, we had commodity money, and it was an answer to barter, which is like direct exchange. And then we gradually moved to indirect exchange, which is this cool way of like binding value in time. Like I'm not gonna put down the down payment for my house and the blueberries that I harvested this year because they're just gonna rot. So with money, it's really a technology. It's a unit of measurement, it's a store of value. I kind of get a kick when people say money is, like, you hear that money is the root of all evil. I mean, there's something in there, but it's like saying like the inch is the root of all evil. It's like, well, it's kind of just a tool. I guess in a way inches are, if you think about like war and geography. Anyways. So like, we didn't want to carry around gold, so we gave gold to this like guy who had a vault. He gave us some receipts, and we realized we could just trade these receipts around and voila, paper money. And then within the last century, we've had money in the form of bits in the bank. So we've just gradually moved away from like physical money, which is naturally more decentralized and distributed. And you have to trust less in, say, gold compared to bits in a bank's ledger. And Sasha really drove this point home. Like, money today is a ledger. And with Bitcoin, we have a ledger, and it's now distributed, and it's no longer at the banks. So it's just that's the wrong ledger, sorry. So it's just like an accounting technology. Here, to kind of go over that really quickly again, is gold has kind of a high storage costs, and it's hard to transact. You don't have to trust it. You just have to trust that people will value it, which historically people have done. And it's not programmable. Cash, we kind of slowly eke down these technologies, and we trade away trust for easier transactional experience and low storage costs. Well, the really cool thing about cryptocurrency is we get like the best of both worlds plus some. We get like very low, no friction. I can send money from here to Singapore, wherever, as long as they're not blocking the internet, or if they're connected to a satellite. That's pretty cool. I actually didn't know about that. And then it's completely trustless, and it's programmable. So it's like similar to like Visa's doing maybe some anti-fraud. So they're able to like program the value a little bit, but now we can do it in like a completely trustless manner, which is quite cool. So there's blockchains and not just one blockchain. You might, hopefully, that's elucidate something. But they are distributed ledgers. That's a really good word to use to describe it. Other things you could use are like, it's a distributed database, it's like shared memory, digital memory, or it's a registry of assets and transactions. Here's a little graph of like, here, this would be PayPal or Visa, and then here's Bitcoin or Ethereum. Everyone has a copy of the ledger here. We need to ask Visa or Citibank, we need to send messages through them if we want to change their ledger. They have to approve it. So with this new type of distributed ledger, its properties are immutability, so it just can't really change it feasibly. Like there are some theoretical attacks that that you can do on a blockchain. Maybe we can get into that in the Q&A. You can only add to the blockchain, so you can only add like a new block to the front. Everything else is just in history. It's very hard to censor people wanting to write or communicate to this network of nodes that's maintaining the blockchain, so it's censorship resistant, and it's always available because there's no like single point of failure server. I mean, really it's not always available if there were like an EMP or a giant solar flare. There's like something catastrophic, but for the most part, as long as like someone's laptop is running in Estonia who thought it would be cool to download the blockchain, voila, it just takes one person and it's still alive. So with the internet came this huge paradigm shift of cheap information. And for better or worse, like we've had a lot of good things come from the internet. I didn't go to college, and I was able to just teach myself a ton of things and get a good job, and thanks to the internet. With blockchain, we now have cheap trust, in a way, or cheap value transference. Cheaper. Okay, so we're going to kind of dive into the technical weeds now that we understand, like, money is just a social construct. It's an accounting technology at this point. And that's why we can put it in ones and zeros and copy it across all of these machines. And somehow that's considered money, and it's being traded for thousands of dollars, even though like a couple of years ago it was a few dollars. It's a little bit mind-blowing. Now, how many people here would say they could comfortably explain what mining is to someone?
All of you after that, right?
Yeah. Okay, cool. That's one of the subjects. Also, who here understands like cryptographic, like public-private key cryptography? Okay, cool. So those are like major building blocks that I'm going to dive into now and get into the technical weeds here. At a higher level, we have like what I'd like to say 3 main components of a blockchain, which involves the network, which is how do we get this data distributed to everyone. It's very similar to like BitTorrent in that way, this peer-to-peer system. And then we have the consensus layer, which is how do we get everyone to agree on what the correct data is. In BitTorrent, it doesn't matter so much if there's like subtitles in the movie you illegally downloaded, or like you're not, but in blockchain, it really matters if all of a sudden you have like 1,000 less, insert cryptocurrency here than you did the other day. You'd be quite angry. So you want things to be correct always on a blockchain. There's no room for error. And the last layer is identity. How do we as individuals interact with this technology? How do we make transactions? Really, how do we send messages to it that can be received by the network and interpreted accordingly? So the first layer, the network layer, is like, who here has used BitTorrent? Yeah. So it's a way to download and share files that doesn't require any central server. It's just purely peer-to-peer. Say that 10 times. Sasha touched on it a little bit. But it's this way where we kind of have this gossip network where as long as you can connect to one node, he or she will have a list of all these other nodes, and you're just like updating this master list that you have, and you can very quickly see the entire network without ever actually having to rely on a central point. So when you're going to like Google Sheets, you're asking Google. And when you're collaborating with people on this like cool thing that Google Docs has now, it's all going through Google, and they can see everything. And it's a central server model. And with peer-to-peer, you're just going direct to the source. It's much harder. Like this is a very censorship-resistant aspect of this style of decentralized / distributed network is very difficult to squash. In America, it doesn't hit us to our heart as much as say in other countries where there's been more censorship and just like more authoritarianism, but to some people it's a very important feature. The consensus layer is like, how do we, okay, so we've shared this data across each other. Now, how do we agree on everyone's account balances, essentially? And this is done partially through the process of mining. I think this is a quote from Nick Szabo, who some people think is Satoshi. The verdict is still out. The consensus algorithm that I'll be touching on tonight is what Bitcoin uses. It's not the only way to achieve consensus, but it is a very elegant, it was the big breakthrough that Bitcoin brought us. And it's called proof of work, or Nakamoto consensus. This was like, mining, back in the day, like anyone could do it. I mean, little did this guy know that, the 5 cent Bitcoin he was getting every couple of hours was, allowing him to like pay for his college tuition or something. But now we've got a little more serious, and we have warehouses full of, these specialized ASIC computers, which are devoted to only doing the single operation that's required to mine, to help mine the Bitcoin network. It's a little bit troublesome, in my opinion. We're devoting massive amounts of power resources to securing this network, this kind of like arbitrary process that is proof of work, of achieving consensus. It's actually very expensive in a proof of work system. Ethereum and some other coins are working on other consensus models that don't require such an expenditure of energy. But this is what's come about from the value of Bitcoin, and we're seeing these things near Icelandic geothermal plants and Chinese hydro dams where they get artificially cheap power because they just built the wrong dam in the wrong place. Now there's warehouses of Bitcoin miners next to them. It's pretty bizarre. It's like science fiction world that we're living in right now. So mining is very similar to a game of bingo, where you're all sitting in this, like all these miners are sitting in this room, and you have to do a bit of work to play it and to win it. And then once somebody does win, they announce it, everyone in the room knows. You bring it up front, it's easy to verify. It takes a bit of work to win, but it's easy to verify that they have won. So it's this whole idea of like, it's hard to win, easy to verify. The most fundamental, crucial point of in my opinion, of wrapping your head around both mining and just how blocks are chained together is called cryptographic hashes. And you can think of it as a data fingerprint. It's a one-way function. It's like this black box, and you take data and you put it inside the black box, and out comes a fixed size number. And because this number is oftentimes in hexadecimal format, it looks like a bunch of numbers and letters. In actuality, it's just a really, really big integer number. So you can take the entire internet and feed it into a cryptographic hash function, and out pops, a 32-bit number or a 256-bit number. It's a fundamental computer science tool. Virus scanners use it. They'll create fingerprints of viruses on the computer, and then when they scan your computer, any file that fits a known fingerprint of a found known virus, they'll be like, that's a virus. They don't have to look in the source code or dig through all the bits of the virus to really know what's going on. They're using this elegant cryptographic hash function. They're essentially, we know that data fingerprint is a perpetrator, remove it. I will show you very quickly. If anyone has a Mac, you can open up the terminal and SHA-SUM, which is the hashing, which is one of the hashing algorithms, is like right in there. So like another key property is that if you change one small thing, it entirely changes how the hash looks. So I'll show you, like, I'll type my name, and there's my name's hash. But if I say do a lowercase d, it's completely different. It starts with different things, it ends with different things. It's like the whole jumble is completely different. Does that make sense to everyone? This idea of a one-way function, kind of a fingerprint. You can literally feed it nothing, and nothing has a hash. Or you can feed it one thing or any number of things, and it's always going to be that same size. So the blockchain is linked with these hashes. We can reference previous data by just hashing it in a very compressed format and then putting it inside the next block. So we take the hash of the previous block and put it inside the new block, and so on and so forth. So everything is chained together in this way. If we change block number 7,200, it's going to change its fingerprint. If we change any single one or zero in that, millions of ones or zeros, it's going to change that block's fingerprint, which is then going to ripple up across the entire rest of the chain, because every block afterwards is referencing eventually that fingerprint. So any change to any block just ripples up the entire chain, and that's one of the ways it's very difficult to kind of hack the blockchain, because you would have to not only get, say, a number of miners to agree that, okay, this block back here, you changed some transaction where you gave yourself $1 million, or you double spent some money, essentially, that you didn't have. But then you'll have to get all the miners to agree on all the blocks afterwards, which is just immensely difficult. So that's why when you're spending Bitcoins or Ethereum, you'll often hear like, all right, wait 6 blocks to be sure. It's kind of an arbitrary measurement. It's like after 6 blocks, the degree to which it becomes difficult to crack, to exploit the Bitcoin network is just basically impossible. You can be reasonably assured that that transaction that you made is now in the blockchain forever. There's going to be no fork weirdness that occurs where all of a sudden you sold your car, you got some Bitcoins, and then you go home a few hours later and all of a sudden those Bitcoins are gone because something weird happened on the network. And if you wait a while, you just wait for it to confirm. So it has similarities to like a Russian doll, where the Genesis block, or the first block that was ever made by Satoshi, is at the very center, and then every 10 minutes a new layer is put on, and it just keeps getting bigger. And we don't have to like send out this whole new blockchain every time. We just send out the 1 meg blocks and we link it to the previous block. So we're saving a lot of like bandwidth and data. Another good analogy that I heard was it's similar to Amber, where you just get layers of Amber over the data, and the deeper the data is in the Amber, the transactional data, the more like it's just going to be there forever. And the nice thing about this analogy is that Amber is, it's clear, unlike the Russian dolls. So you can see all the way down to the first transaction. So it's one of the features of a blockchain is everything is transparent, except for a few novel blockchains out there like Zcash and Monero. You might not know that it was Coury or Evan or Sasha who made a transaction, because they're just going to be some jumble of letters and numbers. You'll often hear this like pseudonymous or pseudo-anonymous. Your public address is not easily linked to your name, but everything is transparent. Okay, so mining. How does mining work? So they have a list of transactions that are sitting in the kind of the cache or the memory, and there's all these previous blocks, and they take the hash of the latest block, and they're trying to mine a new one, and they stick this hash in this say we'll call it this data blob. They stick the previous block's hash in this data blob. They stick a list of transactions, a few other things like the time, and they hash that. And if they get a hash below a certain number, then they win. Like, it's just arbitrary lottery dice rolling. You can imagine a dice with as many sides as like there are atoms in the universe. And they're rolling this dice, and they don't necessarily have to get one single number right, they just have to get below a certain amount. And all of those computers that you saw sitting in that warehouse are literally just hashing over and over and over and over again until they get a hash or a number that's below a certain amount that the network determines. And this determination is made so that new blocks are discovered or rolled every 10 minutes. So if more miners come onto the network, then the difficulty will increase, aka the number that you have to find, that you have to roll the dice for, will get smaller. And if you didn't do that, you could just have a bunch of new miners come on the network, and all of a sudden block times would go from 10 minutes to 2 minutes, because it's just it's just a probability game. The more people rolling dice, the more you're going to get people rolling these lower numbers. So the difficulty is dynamic. And the one thing that they change, because if you were just hashing, a list of transactions and the previous hash, you would just get the same hash every time. If you're hashing the same data blob, then it will output the same hash every single time. So the way the miners add some dynamic, some randomness into the situation is through this number called the nonce. And every cycle, every compute cycle or hash that they run, they increment the nonce number by 1, essentially, or they can randomize it. And when they find the nonce that, along with the rest of this data, creates the winning hash number, they submit that to the network. So this is where it's very difficult to find the answer, but it's very easy to verify the answer for the network. So they spend all this time and energy just with all these computers mining and hashing all this data and increasing the nonce each time. Oh, wrong answer, increase it. Oh, that's not it, increase it. And eventually they land on one. Like in this case, the network difficulty is 9, so anything below 9 wins. Every one of these nonces did not get the right answer. Finally, 99 was the correct number, and you could submit that to the network. They could all verify it in fractions of a second, and then on to the next block is being built. So it's kind of a weird, kooky process. Like it's pretty arbitrary what's happening here. It's just it's economic games. You don't want to spend millions, thousands, tens of thousands of dollars on electricity, on your electricity bill, and then lie to the network. You're doing this because you want to make Bitcoin or Ethereum or whatever. If you lie, if you submit a wrong block, all the other nodes are going to check you. They're going to check your list of transactions, and they're going to reject it if it's fishy, if it's got a transaction in there that doesn't exist. So you're incentivized to not lie because you're spending all of this money you're proving the work that you've done to the network. So there's this kind of a crypto-economic game going on here. Sasha stole my picture. So the difficulty is dynamic. It adjusts every 10 minutes, or it adjusts to achieve 10-minute block times. In the case of Bitcoin, for Ethereum, it's actually 14-second block times. So we have this property of it's difficult to discover it, but it's very easy for the rest of the network to verify it, all because of these cryptographic hash functions. So there's this process of like a miner discovering the nonce, the correct answer, propagating that out to the network. Everyone else kind of like halts there. If they're a miner, they kind of halt, verify it, good. Now they're working on the next block. And people who aren't mining, you can just run a node that's simply validating and verifying what the miners are producing. And you're helping the network out in this way as well. All right, so the last layer of this is identity. So how do we interact with the blockchain? How do we spend money? How do we make sure that someone else isn't spending my bitcoins for me? How are they prevented from doing this, and how am I able to do this? This happens because of the magic of public and private key cryptography. Now I think maybe just one at a time. We have like 10 minutes. You guys can just line up and kind of read this slide, and we'll get through it eventually. Yeah. So encryption before the 1970s was more or less what they called like symmetrical, or in this case, monoalphabetical encryption. And this is like the most classic form of hiding data and sending it to each other. It's called a Caesar cipher. So we twist it in such a way where like we create some code like, all right, if you line A up with T and then pass letters in, you can encode something and you can decode it back out the other way with the same key. So there's this symmetrical property going on here. So if we take Caesar cipher and ran it through this wheel, it would create, and then Cthulhu will rise from the field behind us. So we have this, with symmetrical encryption, there's this very big problem, and this was in World War II and all the great wars, like where we had to do key exchange. So like on the submarine German U-boats, they had binders full of keys for the Enigma machine. The Enigma was symmetrical encryption. It was complex symmetrical encryption, but nonetheless they had to exchange keys, and it was very hard. You couldn't do it over the radio waves because, well, everyone was listening to the radio waves. So there's this image of like two people in a park, like secretly. There's all these great stories of medieval times of like when key exchanges go wrong. There's probably a whole book on that. Now, after the 1970s, this amazing mathematical discovery allowed us to do what's called asymmetric encryption, or public key cryptography. And it's essentially where you have two keys now. One of them's public and one of them's private. And you always keep the private one. You never release that to the public. And you just put your public key out there as far and as wide as possible. And what happens is you encrypt things with your private key. And then you send it to someone, or I guess the other way around. You encrypt something with someone else's public key, and then they are the only ones who can read that message because they decrypt it with their private key. You can't encrypt and decrypt something with only one of the keys. One key is for encrypting and the other one is for decrypting. And you can kind of send it in either way, but there's this asymmetrical quality to this. So this gives us this like really cool feature of no longer is cryptography or this style of cryptography used for hiding information. You can use it to verify your identity. So you have a public key, you give that out to the world. You take your private key, you sign a message with it. So you write a little message, then you encrypt it, and you send this encrypted message out in the world and say, yeah, this is me, and they'll take your public key, and if that message decrypts to something sensical, like a sentence or something, they know indeed, like, okay, Coury owns this public key. We've tied that key to his identity. So this is how it works on the blockchain. Is your Bitcoin address is a public key. And when I send money, like my mom donated money to the Meetup group tonight, well, she sent it to the group's public key, and only I can spend that with my private key. And the spending process is like you're literally just writing a message that the Bitcoin protocol understands, and it says, like, I want to, Coury's mom wants to send Coury, whatever, Bitcoin. And then it encrypts that message, and the network decrypts it with her public key to verify that she was the owner of those Bitcoins that are associated with that public key. If it decrypts to a bunch of like jumbly wobbly-gook, then it's no good. Like she's clearly not the owner of that private key which holds those Bitcoins. That's a little dense, I realize. Does anyone have any question? Like, I want to elucidate that more. Yeah.
I'm very confused, like, as to how the transactions are like associated with the hash, if it even is.
So the transactions aren't associated with the hash per se. They're associated with someone's key. And you can go on a block explorer and you can type in someone's public key and see how many Bitcoins they have. And the network, kind of at a protocol level, knows this too. It's in the ledger. So if you want to be able to spend those Bitcoins, you have to have the private key corresponding to that public key, which can take a, hey, I want to send Bitcoins message, encrypt it, sign it. Not because you're trying to hide data, but because you're trying to prove to people that you indeed own those Bitcoins that are associated with this public key. And when you send this signed message out to the network, it's decrypted, which is kind of how it gets validated. It decrypts into something that the Bitcoin network understands, aka I want to send Bitcoin. Then all is well, you've been validated, you own the private key. There's no way to spoof that. Yeah?
Just curious, what happens to the mining sites and the security around the actual physical building? So say there's a bomb goes off, what happens with all those keys that are going back and forth?
So key management is definitely, there's not a lot of keys going back and forth per se. Everyone's private, that's why it's like everyone's private key is, they hold it themselves. If you have a wallet on your phone, the private key is on your phone, no one else knows it. So private keys aren't really moving around a lot. Only public keys are, which is fine. So the mining sites, like that's just a matter of how they decide to do with security. Key management is something that's been happening in the IT world for decades, well beyond Bitcoin. Public-private key cryptography, is like every time you open your browser and you see the little green shield in HTTPS, that's using the identity feature of public-private key crypto to make sure, like, yes, this is actually Google. Like, they're not. It's also using the encryption feature as well. But yeah.
Could you lose your private key?
Absolutely.
Is there any way to recover it?
No. There are ways in which you can set up safeguards or backdoors, but as far as actually losing the private key itself, there are ways you can recover it through hard drive forensics and whatnot. But if you lose it, you cannot spend that Bitcoin, and you never find it. There's no other way to spend the coin unless you have the private key. There's a lot of techniques involved around key management, like I said, so it's not like the end of the day, but that's definitely an issue.
That's an important question too, because when we talk about 21 million Bitcoin, that's the theoretical maximum, but we also assume that millions of Bitcoin have already been lost because they used to be worthless, so people just kind of like threw away these computers, and now we don't know how much Bitcoin is actually in circulation.
Here, Sasha, so it's pretty much Q&A time right now. Can someone maybe hit the lights up just a little bit in the back, and we can kind of open it up? Yeah, gentleman in the back there. Yeah.
So you said when the miners are working on a group of transactions, they all on the same transactions? You said there's a mempool of unverified transactions. How do they select the ones that are
Typically, it's done through, they rank it by transaction fee. So they want to make the most money. That's why the lower transaction fee you use, the longer it takes to get validated on the network.
It's so follow-up, if a miner is working on maybe a lower group, could they get their that block verified?
Yeah, so like usually all the transactions are sent around this gossip network, and this list of transactions is huge. You can only work on a certain subset of it because you can't go over a 1 meg block.
Right.
But for the most part, everyone's transaction pools are in sync.
Let's do like 2 more questions. I think this group's small enough to where we actually have a handful of experts in the room. Those of you who would acknowledge yourself as an expert, raise your hand real quick. Yeah, so they're all sitting on this side of the room.
Yeah, why don't
And
while we answer some last questions.
We'll do like 3 more questions, but then we could just split up.
Yeah, the experts, one of you come up here, and a couple in the back, just right now. And lady in the back, yeah.
This is probably a basic question, but you were saying like someone, you wouldn't want to lie or talk about truth, but
Yeah.
with blockchain, like you can't actually verify that some things like actually happen, right? So you can put anything on there Tesla could pay Andy $5,000 to buy Coors Field, and someone else could pay someone else $5,000 to buy Coors Field. Like, how can you verify who?
That's a great question.
Coors Field? Like the truth, I guess.
Yeah, we can't necessarily verify the truth. We can just verify what's recorded, and then we all have to acknowledge that this is the truth. So when we talk about chain of title for something like real estate, we all have to first acknowledge it. This is the chain, and we all have to register our real estate there to begin with, right? So we can't both buy the same property unless someone's signed off on it first. So they had to have proven ownership to begin with.
But the blockchain would allow that. Like that could.
No, we still need a third party like government to say like we've registered all the properties here, these are all the owners, and then we have a starting point from there where it all can be recorded on the blockchain. There's a project called Augur. There's a project called Augur, and Augur is a predictions market, aka a betting pool. So the idea is you'd be able to predict the future if you gave people a place to bet money on whatever the future is. So if we said, is it going to rain tomorrow? I need to know because I'm a farmer. Then I would create a betting place for will it rain or not. The betting place exists on the blockchain. And then theoretically meteorologists would start betting because they maybe have some kind of special insight. But then after tomorrow happens, you have to verify, well, did it rain? And for that, Augur depends on a network of what they call oracles. In oracles, they put money at stake to say that it did rain, and then once there's a consensus among the oracles, then it's verified that it did rain, and if one of the oracles somehow lied, then they would lose the money that they put at stake. Yeah, it gets complicated.
Yeah, what's up, Ryan?
The question is about value, because I think a lot of folks that have kind of entered the space, have kind of looked in from the outside because of the value of a lot of these cryptos. How does the value essentially get determined on a lot of these?
Yeah, so that's like economic question. It's really, it's supply and demand. That's it. No, value is subjective. I mean, if you talk to the Austrian school, if you talk to the Marxists, they think it's the amount of labor you would put into something. I don't necessarily think that's true, but there's something in the middle there where it's like ultimately it's the human valuing something. You go to an art show and you see some piece of splatter that cost $1 million or whatever. You don't value it that much, but somebody does, and it's largely, in this case, it's utility. So Bitcoin, didn't have any value in the beginning, but then its utility was understood over time. Like, oh my gosh, this has a lot of utility, and therefore, it has utility. It has scarcity. Ergo, it has value, and it got a market price, and there was an exchange, and prices were determined. There's a number of buyers who created the buy side of the order book, and there's a number of sellers, and with this process, you get kind of a market price. Now there's a ton of exchanges, and they all have their own order books, and they all tend to be in sync with each other, because if there's any disparity between them, you'll generally get actors who who are doing transfers across. This is called arbitrage, and they're making money on this. So you get this kind of market price. And at this point, it's like, this is valuation, and it's like highly suspect sometimes. It's, we get these massive swings, and a lot of it is hype driven right now. But
Yeah, so the question is this a crazy bubble, right? I said we wouldn't be talking about investing. But the question is, how do people value this stuff? And I reference a really simple stat, which is, right now, I remember that math, the mining reward, 12.5 Bitcoin per block, and a new block every 10 minutes. So that amounts to 1,800 new Bitcoin created every day, 1,800. Coinbase, one exchange, but the largest US exchange, they have a public counter that shows you how many new accounts are created. And to open an account on Coinbase, you gotta submit your driver's license, you gotta jump through some loops. So every new account equals a real human. Coinbase every day has been opening over 10,000 accounts. And that's just one exchange, right? So 10,000 accounts on Coinbase chasing 1,800 new Bitcoin per day.
one thing I do want to point out, actually, that people who are just getting into this is, in Bitcoin, there's a long history, or in the cryptocurrency space, there's a long history of exchanges getting hacked or exploited. The security and technology around this is a lot better than what it used to be. It's kind of more Wild West back in the day. But the distinction to be made here is when you have your money on a service like Coinbase, they hold the private keys. So they are a trusted third party. They are being your bank for you. They could get hacked. Something could happen with Coinbase. You don't own you really don't own your Bitcoin or Ethereum or Litecoin or whatever in the true sense if it's on Coinbase. That's fine. I mean, your money's in your bank. You don't own that. It's not cash. But the cool thing about Bitcoin is it's really easy to be your own banker, to hold your own private key. Now, to his point, you don't want to lose that private key. So you want to be very stringent about backups and how you back it up. And there's hardware wallets that you can buy. There's a lot of ways to back up your private key, but just be wary of leaving your money on exchanges especially a lot of money for a long time, when it's so easy to be your own banker. And I think it will just get easier as key management kind of user experience gets better.
Let's do one more question, and then we'll split off into our groups. We'll hang out here for like another 20 minutes or so, and then whoever wants to join us, we'll walk down to Blake Street Tavern. Sound good?
Yeah. I was just going to say, can't you also just print out your private key onto a piece of paper?
Yep.
Any other questions? Yeah.
I want to get Bitcoin with Ethereum with the cash. What is my option?
Localbitcoins.com or localethereum.com. It's like the Craigslist of being able to do these cash transactions. Or you can go to a Bitcoin ATM, which you can. There's some coffee shops around Denver and Boulder, and you can put in cash. You put up your public key that's like on your phone, and the QR code will scan it and it will send you
The question was, how do I buy Bitcoin or Ethereum with cash instead of going through someone like Coinbase? And there's two websites that facilitate that: Local Bitcoin, Local Ethereum. Or you can talk to one of your buddies.
Break it up, Sasha. Let's plug. So we've created this site to kind of centralize some of the information there. It's called coloradoblockchain.com, and here we've connected with a bunch of the other meetups in Boulder and Denver. There's chat channels, Slack chat channels. All the meetup information is on coloradoblockchain.com. A few other things, so just write that down if you want to get in the chat rooms, talk to people, learn more, come to more meetups, and I think we'll break it up if people want to hang out. I guess experts, as people get up, just raise your hand and form little groups. We'll see how this goes. Maybe be a little chaotic. Yeah, thanks everyone for coming tonight.
Thank you guys. Thanks for calling.